Hey, Science Nines, Manchak here, with some really funky stuff going on the video there. I'm here with your Concept D4 video lesson that we are going to run through over the next few minutes here. But before we get into that, I want to make sure that you guys have covered everything you need to cover to this point. So if you haven't gone through and done this, this is where you should be at, and a little bit of a review for you. We started out in Concept D1, which had us looking at static and current electricity, some electrical safety, as well as things like cells and batteries. We then moved on to talking about Ohm's law and controlling current, measuring electricity, and actually quantifying, putting some numbers to it. And then we did some electrical circuit work as well. And some of you have handed in, but not all of you, the electrical systems, the circuit lab that I did with you. So if you haven't done that yet, have a look at it. I think it'll be beneficial for you to work your way through that. We then moved on to Concept D3, and Concept D3 had us looking at energy forms and transformation, so different kinds of energy, as well as how energy transforms from one form to another. And then we looked into the link between electrical and mechanical energy and how we work with things like generators and motors and how they work and why they're important to us. So where you're at right now is we're moving into Concept D4, which is a little bit, it's a relatively short concept where we're going to explore how we measure things like energy input and output. So we're going to actually introduce a couple new formulas here, like the formula here, P equals IV, like E is equal to P times T. All of those are going to get used as well. And then we'll talk about the idea of conservation of energy and how that relates to energy efficiency. And we'll play around with those a little bit. So that's what we're going to cover in this concept today. I'm just going to switch the window here and show you that this is sort of our general breakdown of what's going on in this concept. So we're going to measure, we're going to see what power is and discuss what power is, how we measure it, how we work with it. We're going to link power to energy. We've talked about energy before a few times. We'll talk about the law of conservation of energy, which is a big idea in science, so pay attention to that. And then we're going to relate energy to efficiency, and then we'll work with efficiency and play around with another way we can calculate efficiency. And then we're going to finally talk about reducing energy waste. Textbook pages, videos, formative work are all going to be posted just above where you found this video in the Google Classroom, so you can track that as well. I've got 4 videos for you to look at, and I will make reference to them as we move through the video lesson here. And then we've got some practice questions out of the textbook, a worksheet that if you'd like to, you can work your way through. And I may put an activity up. I haven't decided yet. I've been playing around with an idea in my mind, and we'll see if it's waiting for you when you get this video or not. And then lastly, we'll have a practice quiz. Please remember, as always, do the practice quiz before you do the summative quiz and wait for that feedback on the practice quiz before you move on. So I think without any further ado, I'm going to switch over to my PowerPoint here, or my Google slide here, and I'm going to get us up and rolling with that and move my video off to a corner and make it a little bit smaller. You'll notice I've got a little bit different setup today, playing around with something new and see how it works. If it's not working for you, then by all means track me down on my office hour or fire me an email and say, hey, I like this or I didn't like this, and we'll play around with it that way. Okay, so where we are moving into now, Concept D4 is dealing with all the stuff we've talked about there. And we're going to start out first by talking about energy input and output and how we can measure it. Remember, we're still talking about electricity here. So we're really talking about devices that have energy, electricity coming into them, and then what are we putting out as far as the energy that goes out. And so a lot of this has to do, and we'll have you thinking back to what you've done in previous courses, particularly in Science 8 last year. Because we did talk about simple machines, machines that allow us to do amplify the energy that we're putting into something, something like a lever or a pulley, or we're moving into talking about more complex machines. And I would argue that these electrical devices that we're going to talk about are machines. And so we want to try to minimize the amount of input that we put in and maximize the amount of output that we get out. Okay, so that's sort of where we're playing around. So think about some of those machines that we use, some of those devices that we use that use energy in some way. So at this point, if you wanted to get a good introduction to what we're doing, there's a 3-minute and 33-second video called Energy, Work, and Power. You can hit pause, go into the Google Classroom, click on the link there, and give that a watch. Remember, those videos are all under D4, resources, videos, etc. So if you want to do that, go right ahead and hit pause now. Okay, I hope you enjoyed the video, and I'm going to move on. So the first thing I want to talk about today is power. And what is power? And we talk about this quite a lot, actually, in our lives. You know, this vehicle has so much power, or, you know, this thing is very powerful. But when we're talking about electricity, power is slightly different. And it has a slightly different connotation when we're dealing with it. So I want you to think about power as the rate at which a device converts energy. That's a kind of interesting consideration. Okay, the rate at which a device converts energy. So how much energy is it converting per second? Okay, so remember that rate that we see here, we're referring to rate as how quickly something is happening. So in the case of power, power is measured in watts, and a watt is a joule per second. So remember, if you don't recall this, a joule is a measurement of energy. Okay, so it is a measurement of how much energy is in something, or something is creating or transforming, or whatever we want to say. And so a joule per second is a watt. So how much energy per second is the device converting? So think about a speaker, because I think a speaker is a good way to look at this. A speaker is often measured in watts. You know, you'll have a very small speaker, it might only be a 10-watt speaker. So it's converting about 10 joules of energy per second. You have a big speaker, maybe it's a 100-watt speaker, it's converting 100 joules of energy per second. In that case, because we're talking about a speaker, it's converting electrical energy to sound energy. Okay, so we're getting that conversion taking place, and that key word up here is conversion. So for an electrical device, we can actually do some measurements associated with some of these variables. You should be familiar with you. So first off, we represent power as a P, and then you guys should know these two variables as well. I is for current, V is for voltage. So for an electrical device, power is equal to the current multiplied by the voltage. So I gave you a little triangle again, even though I'm not a big fan of triangles. We're going to use it anyway, just to keep things simple, given the state that we're in right now. So P is equal to I times V. So if we multiply current, which is measured in amps, by voltage, which is measured in volts, then we should end up with the power that the device works through. If you're curious, we could actually figure that out sometime. You know, come on office hours and I'll show you how that actually works with some interesting algebra. But for now, we're just going to leave it at that. Remember how this works then is that if we want to figure out power, it's current times voltage. And so we'd cover up P and it'd be I times V. If I wanted V, it'd be P over I. If I wanted I, it'd be P over V. Okay, so what we're going to do now is I'm going to switch over to the next slide and then set up my quote unquote document camera, and we'll work through an example together. Okay, so let's switch to the next slide, and you guys should have this in front of you. I'm going to drag this in, and then we will maximize it, and we can see what's going on. So our example says a hair dryer has a power rating of 1,000 watts. If it is plugged into a 120 volt outlet, what is the current flowing through the hair dryer? Okay, so as we did with other questions before, let's analyze the question and figure out what we've got. So I see a power rating of 1,000 watts. So as soon as I see power associated with this, I see the unit watts. I already know that my power in this question is 1,000 watts. So we're not being asked to figure out what power is. We're being asked in this case to figure out what current is. So the other thing it tells us, if it's plugged into a 120 volt outlet, volts, remember, measures voltage. So V is equal to 120 volts. And then it asks, what is the current? Okay, there's our question. So I is what we're trying to figure out. Remember our little triangle. that we set up on the previous slide. P is equal to I over V. What we're interested in is I. Put your finger over top of it. That means P over V is how we're going to figure this question out. So I'm going to take P is equal to I over V. And then I'm going to substitute my numbers in. P for power, or sorry, I. Well, that's completely wrong. Let's figure that out. Let's try that again. Thank you for those of you that were yelling at YouTube right now and saying that that's not right. I appreciate that. I heard you, and I'm going to fix that. So instead, we should be doing I is equal to P over V. I'm going to leave that in. I'm not going to edit it out because it was kind of funny, and it just shows you that I can still make mistakes, and I make a lot of them. So P, we figured out up here, is 1,000 watts. So we'll put that in as 1,000 watts. And then we have V, which we figured out over here, which is 120 volts. Okay, watts over volts is going to end up giving us amps. And then we snag our calculator. Okay, got my handy dandy calculator. I'll put it up here so you guys can see what I'm doing. We'll do 1,000 watts divided by 120 volts. And that is going to give us I'll do it to 1 decimal place, 8.3 amps. That's a really terribly drawn 3. And then I like to put a box around the answer so then I know that that's where I'm at. Okay, so the key bits to understanding this then, make sure you go through and determine what your current or what your question is telling you. So it says it's a power rating. Remember to look at the units because the units tell you what variable you're dealing with. So in this case, we're dealing with watts, right? And then we're dealing with volts. So that tells me that we have power and voltage, and we're trying to figure out current, which is what the question is asking. And then we'll ignore the screw up over here. And so current is power over voltage, 1,000 watts over 120 volts, which is 8.3 amps. So I hope that makes sense to you how we did that. I'm going to shift us back to our PowerPoint over here, or our Google Slides, and we're going to continue on. So what I promised earlier on is that we're going to spend some time trying to link power to energy. And we kind of did already, because we said that power is the amount of joules per second that a device is converting. Okay, so then we can start to use the power rating of a device to determine the amount of energy that that device uses. Because if we know that a watt is a joule per second, basically, you can then do a conversion and figure out how much energy that device might use if you use it for X amount of time. So you may have done this before. You may have noticed that if you look on the back of some electrical devices, there's often a tag on those electrical devices, and you can find the power rating on those devices. So what I've done is I just went and grabbed for you something that I have in my house that I work in my basement now, and it keeps me warm, is this space heater, this very dusty space heater. And on the bottom of this very dusty space heater, I'll put it up there for you guys to see, you can see that it actually has a power rating. And I'll put my finger on it and show you that right above my finger there is the power rating. It says 1,500 watts. And I don't know if you guys will be able to see that on the YouTube video, but this device tells me that it has a power rating of 1,500 watts, which means it's using 1,500 joules per second of operation. So that doesn't mean an awful lot, but I'll tell you right now that a power rating of 1,500 watts is very high. And things like space heaters and microwaves, they have very high power ratings. So they use a lot of electricity to do what they're supposed to do. Excuse me. So in order to figure out how much energy is actually used, what we need to do is we multiply the power rating of whatever device we have by the time that we're operating the device for. So for that space heater that I have down there, it's got a 1,500 watt power. It is a 1,500 watt power supply, or it pulls that much power. So it's pulling 1,500 joules per second of operation. So if I operate that over the course of a day for a few hours, and I multiply that by the number of days that I might operate it in a month, I can figure out how much energy I've used. Why this is important, I'll get to in a second, is that it's sort of how our electrical companies determine how much money we pay for electricity on our monthly bill, because they measure how much energy we use over the course of a month. So anyway, I digress a little bit. Energy, remember, is measured in joules, and in this case, time will be measured in seconds. So we may have to do some conversions at some point that bring us away from joules and back to, or sorry, away from seconds and back to minutes, or vice versa, depending on the situation that we're being placed in. So what we're going to do is I'm going to do another example here for you. So we'll go, this is our second example just to show you how to use this formula. So I'll drag my screen back in here and we'll get it maximized and have a look. So a microwave oven has a power rating of 800 watts. So there we go, right away there, 800 watts. And honestly, you could do that. Pull your microwave out. You know, do so carefully without knocking anything over, and look in behind it. And then while you're in behind it, do your parents a favor and clean in behind it, because they probably never do it, and I know I don't. And see what your power rating is. This microwave in this question is 800 watts. I would imagine that some of the ones we use are higher than that, 1,000 watts, maybe more. If you cook a roast in this oven, I like spelling mistakes, for 30 minutes at high, and we'll assume that high means that we're operating at the full 800 watts, which you guys can't see what I wrote over there. Okay, I wrote 800 watts over here. At high, how many joules of electrical energy are converted to heat by the microwave? So much energy did it consume. So what we know in this question is our 800 watts is our measurement of power. Okay, and our measurement of time, I'm going to put as a lowercase t, is 30 minutes. Now remember, our formula suggested to us that we need to be using time in seconds. So in order to convert time to seconds, you need to ask yourself how many seconds, sorry, let's try that again. In order to convert minutes to seconds, you need to ask yourself how many seconds are in 1 minute. So I would say to myself, well, there are 60 seconds in 1 minute, right? 60 seconds in 1 minute. So then that means over here that if I have minutes on top and minutes on bottom, those minutes cancel out, and the unit of time measurement that we're left with is seconds. And so 30 times 60 is 1,800 seconds. So then we go back to our formula to sort out how that is. And just to recall, you jump back over here, and energy is power times time. Okay, so I'm going to go bring my screen back over here. So energy in our little triangle is power times time. Okay, and I'm interested in energy, so I'm going to cover that up. Okay, maybe I'll cover it up that way. And so that means I'm going to be multiplying power by time. So energy is power times time, which is going to be 800 watts times 1,800 seconds. Okay. When you guys get into grade 10 and beyond, I always like to teach a little bit about how units work. Remember, a watt is a joule per second. And if we take a joule per second and multiply it by seconds, seconds are canceled out because there's one on the top and one on the bottom, and we're left with joules. That's how this works. That's why this formula works the way it does. Then you grab your calculator. Now we're going to end up with a large number here. And I'm using a graphing calculator, which means it's probably going to pop up in scientific notation. No, it didn't. Perfect. So now the number that we're given is 144, and then 4 zeros after that. So 1, 2, 3, 4, and then that's going to be joules. Okay. So 1,440,000 joules is what we ended up with consuming if we operated to cook a roast in a microwave. Please don't do that. That sounds disgusting. We converted that much electrical energy into heat energy using the microwave. So the purpose of the microwave is to do an energy conversion, electrical to heat energy. And we used 1,440,000 joules of energy to do that, okay? Which is a fair amount of energy if you think about it. But it's not actually as much as you think it is. It looks like a lot, but really, how much is 1 joule of energy? That thought I'm going to leave you with, and if you want to look it up on the internet and sort of tell me, well, what is the equivalent of 1.4 million joules of energy? Give me an idea. Is that as much energy as a stick of dynamite blowing up? Is that as much energy as you would consume or convert riding from your house to the grocery store, depending on where you live, or your house to your neighbors, right? Tell me, go look it up, see if you can figure it out. Fire me an email, let me know if you can figure that out. So that's how we use this formula. Energy is power times time. So where we've been and where I want you guys to understand where we're at right now is we're just talking about how we can quantify, put numbers to the amount of energy that a device uses in its operation. One way was to look at power, the number of joules per second that it's using. Another way is if we know the power and we know the time, but we don't know the energy, then we can multiply power by time and we can end up with our energy consumption of that device. So where we're headed on to now is it doesn't take long. So if you want to measure this energy, it doesn't take long for devices to consume a large number of joules, right? We saw in the last example 1.4 million joules of energy to use a microwave for 30 minutes straight. This is why electricity and gas bills typically record usage in larger units, right? If we were going to take everything, our energy consumption on our power bill and measure it in joules, we would have ridiculously big numbers that either we couldn't write out on the bill or people just wouldn't understand what they meant. And so electricity bills tend to use something called a kilowatt hour. So it's basically another measurement of energy because we're taking power in the form of watts and multiplying it by hours in the form of time. Kilo, please. Kilo is a modifier, a prefix that means 1,000 of something. So 1 kilowatt, kilo meaning 1,000 of something, so it means 1,000 watts. So 1 kilowatt hour is 1,000 watt hours. Okay, so a kilowatt hour is what we get in our power bill, measuring what's going on. So for our microwave oven, it means that it is using 0.8 kilowatts. Now, if you understand that, that's 800 watts divided by 1,000 to turn it into kilowatts times 0.5 hours. So it used about 0.4 kilowatt hours of energy. So that 0.4 kilowatt hours of energy doesn't seem like an awful lot on the front, but you have to remember that that's just one device operating for 1/2 of an hour in my house over the course of a month. What I have here, and I'll just hold it up and kind of show you, is the power bill for my house for the last month. And just to show you over here, got to go down, my energy consumption was 717 kilowatt hours. Okay, so that is all of the devices in my house that are drawing electricity at any point. So right now I've got a light up here that's illuminating my face. I've got the webcam. I've got the 2 monitors going. My computer is running. I've got another set of lights back over here. All of those are drawing power, and all of those are consuming certain amounts of energy that we are going to measure in kilowatt hours. And what the electrical company does is they have a meter on your house that measures how much energy you consume, how much power you consume over the course of a month. And then they take that number, and you can see on here that they've actually got the reading on here of what the readings were and on what dates. If you could read that, you probably couldn't. What I could do is be a smart guy, and I could make this a bit bigger for you. So you can sort of see on there, if you read carefully, we've got reading on March 28th, reading on February 29th, reading on February 21st, all of that kind of stuff. It's funny how those dates are out of order. And what those readings are, and then that total of kilowatt hours. And then down here, what they're doing is they're multiplying the kilowatt hours I've used by what they're charging me for that energy. So they're charging me for 1 month, they were charging me for at 6.991 cents per kilowatt hour. And then the next, in February, they were charging me more, 8.572 cents per kilowatt hour. Might be something you guys want to have a look at. Maybe track down your power bill at some point and see what that actually looks like and what you're being charged for power and how much your household is consuming. You have to remember, I've got a relatively small house. There's 3 of us that lives here plus a dog. So my wife, my daughter, and me, and we are relatively energy efficient, right? I'm using LED light bulbs. We have relatively new appliances upstairs with our kitchen and downstairs with our washer and dryer. So all of those things make a difference. But I also have a fridge down here that sits mostly empty a lot. That's not saving me a lot of electricity. We're going to talk more about that in a second anyway. So that's how electrical companies do it. It's a little bit different when you get into gas companies. They tend to measure in gigajoules as opposed to kilowatt hours. And a gigajoule, remember, or in case you didn't know, the prefix giga, so that capital G here, represents a billion. So a gigajoule is a billion joules. So that gives you an idea. If my power or my gas company is measuring in gigajoules, that gives you an idea of how much gas I might be using and how much energy is stored in that gas. So of note on here is another one of the videos you can look at, go into the Google Classroom, on how behavioral science can lower your energy bill. It's a TED Talk. It's really kind of interesting. Not required, but hey, if you're wanting to save some money, and who doesn't, might be a good way to have a look at, or a good reason to look at that. So what I want to get into now is talking with you about the law of conservation of energy. This is a big idea in science, okay? And you're going to hear me talk about it this year. You'll hear talk about it in grade 10, 11, 12. It's going to go all the way through. So this is what we call a big idea in science. And the law of conservation energy is important. And it states that energy cannot be created or destroyed, only transformed from one form to another. And I think, having said that, you'll recall me basically saying that I said that to you back in the last concept when we were talking about energy transformations. This is a big idea. It is super, super important to understand the law of conservation of energy. So all the energy that we have out there in our universe right now is all the energy we've got. And so what it's doing right now is it's changing forms. We're converting it from one form to another. So your vehicle, which operates off of gasoline, operates off of an energy conversion, where you take the energy that's in the gasoline, you burn that gasoline, and we transfer chemical energy into kinetic energy, which is really mechanical energy that causes your engine to operate the way it should. So why we talk about the law of conservation of energy in this context is that we're talking about what's going on with converting energy in electrical devices. How good are those devices at converting the energy? What we know is that no device is perfect at converting energy. You cannot get 100% energy conversion. There's always a little bit of energy that is considered to be lost or not useful. So most often the energy we cannot account for, the stuff that is lost or not useful, has been dissipated as heat or sound or light, or created by friction and lost to the surroundings. So thinking about an engine heats up. Well, why does it heat up? Because there's friction in the engine. And that friction is lost energy. That energy that's being generated is being lost as parts of the engine rub against other parts of the engine. We use oils and other things like that to reduce the friction, but it's still not perfect. In electrical devices, there's energy that's lost in the transmission of the electricity or in the sound that the electrical device makes. Think about your blender. It makes a bunch of noise. That means that when that motor is operating and spinning in your blender, it's not 100% of the electrical energy that's going into the blender is being used as energy to spin the little blade. Some of it is being lost to the surroundings, and we are not using that sound energy in any useful way. Hope that makes sense to you. So what I'm leading up to is talking about this idea of efficiency. Okay, how efficient is the device? How efficient is it at taking the energy that's being put into it, what we would call input energy, and converting it to output energy, the useful energy that the device creates. So the efficiency of a device is the ratio of the useful energy that comes out of the device compared to the total energy that went into it when it operated. Okay. It usually is represented as a percent, and here's your formula. So percent efficiency is your output energy divided by your input energy times 100%. Okay, so I'm going to just slide this over here. So in this example here, for an ordinary light bulb, so I'm thinking of an incandescent light bulb, which we don't have many of them around anymore. They have that little coil of metal inside them. 5 joules of light energy is created for every 100 joules of electrical energy supplied. So that would be 5 joules on top divided by 100 joules on the bottom. Multiply that by 100, you get an efficiency of 5%. So in a regular incandescent bulb, the ones that we're trying to replace with LEDs and compact fluorescents, mostly LEDs now, 95% of the energy in those incandescent bulbs is being lost as heat. That is a lot of wasted energy. That's a lot of energy that's going into the room and not doing anything for you. Wouldn't you want to save that energy and save that money that you're spending on that electricity and use it for something else? It's an interesting thought. So that leads me into talking about energy transfer and efficiency. There's a really short video that I've linked in the Google Classroom that you should have a look at, minute and 8 seconds long. Hit pause now. Okay, and I hope you enjoyed the video. That's really goofy. All right, here we go. What's happening here? There we go. So at this point, if you wanted to go, if you haven't watched the video, go watch it and then do a couple of practice questions on page 338. Instead am going to move on to the second half of this concept, and it'll hopefully go a lot faster. So what can we do to reduce the energy wasted by devices? This is the big question for this section. And I've already alluded to some of this, so I'm going to go through it relatively quickly as we move forward. Reducing energy waste is a big thing. And to me, the best way or the best reason why we would want to reduce energy waste is to save money. Really, when you think about it, remember the power bill I showed you, right? That power bill tells me that I'm using this much energy. Well, how could I use less energy? Because then if I'm using this much energy on here, then that means that I'm paying for all of that energy. So how could I reduce the amount of energy that I'm using? So here's some things that you can do. All large appliances like refrigerators, washers, dryers, etc., they in Canada must come with an EnerGuide label. Okay, and an EnerGuide label clearly states how much energy the appliance is going to use on an average month with average use. Okay, this allows us as a consumer then to compare one device to another. And if energy efficiency is high on your list because you like saving money and not spending too much on energy, then that's a great bonus. And you can look at all of the different models that are out there and find the one that you can afford first, and then second, the one that uses the least amount of energy. So you can make a more informed decision when you're purchasing appliances. By the way, we bought a furnace last year at our house, and we compared energy efficiencies of furnaces, and we got one that was 98% efficient, meaning that almost all of the energy that goes in or comes into the furnace as natural gas is being converted to heat energy that's going into my house. So that's pretty cool. Then there's a quick video here on understanding energy efficiency labels. You've probably seen them. It's probably worthwhile having a look at them as well, just to keep up to date on what they look like. I've included this on here, and there's a couple of things I'll point out. This is what an EnerGuide label looks like, and it tells you, in this case, not per month, but per year, how much that device is going to consume. And then usually they have a range on here of how much energy on the low end the device might consume and how much on the high end it might consume, and then the average, where this model would fit from the most efficient to least efficient devices. What I have over here is actually the label that we got done at our house last year when we had an energy audit done on the house, and we had somebody and come into our house, which is a relatively old house. It's 50 plus years old, probably close to 60 years old now, and come in and do basically a whole bunch of testing in the house to determine how energy efficient our house is. You'll notice that we've got the same kind of EnerGuide label on here. They're very similar. And whoops, I don't know why I jumped there. And we ended up with 182 gigajoules of energy being used per year. And then it was really neat as it gave us a breakdown of what is being used. Where's my energy consumption coming from? Most of it's coming from heating our house. We have a lot of winter. It gets cold. There's lights and appliances makes a small amount. Ventilation makes a small amount. Water heating is relatively high, and that's something we haven't replaced recently. So that might be another device we'd look at, and all of that kind of stuff. And so this gave us an idea of how much energy we add up from natural gas and from electricity. And then that gives us a baseline to figure out what we can do to save money. And so one of the things that we did is we replaced our furnace after the energy audit. And and I will tell you, we saved a lot of energy over the winter. So something to look for if you go out appliance shopping at some point, look at these, because now you know what the heck they are. So I've already said this, there are limits to efficiency. It's possible for an electric heater to be 100% efficient, but electrical devices can never be 100% efficient. There is always a little bit of energy lost somewhere along the way to sound, to light. You have to remember that. We cannot break that rule. You cannot be 100% efficient. Any sort of movement creates friction, and a certain amount of thermal energy as a result. So that means we lose a little bit of electricity, or a little bit of energy in that conversion from electricity to whatever other energy form we're dealing with. All right, last slide. Yeah. So if we wanted to increase efficiency, that is a big thing that's going on in our world today. Is there's a lot of work that's going into trying to find ways to make our products more efficient so that we can save ourselves money. And the added bonus of that, I think in my mind, the most important part of that is we're not only saving money, but we're also saving on the damage that we're doing to the environment for various things. So, you know, if we're trying to find the most efficient vehicles possible, that means that we're using less gasoline, which means that we're not putting as much carbon dioxide into the atmosphere, which creates less pollution. Hey, it's a win-win all the way, because you save money and you save the environment, or playing a role in saving the environment. So increasing the efficiency of a device depends on its purpose. Many devices are designed to convert electrical energy into mechanical energy, where the largest energy waste comes through friction. Okay, that's when we have mechanical energy, usually there's parts that move past each other that creates friction. The easiest way to increase efficiency is by decreasing friction with improved bearings or lubricants. Okay. Some of the best new vehicles out there on the market, the electrical vehicles, have a lot fewer moving parts in them. And that's one of the reasons why they are so efficient, is that they have much less parts moving, so they generate much less friction, which makes them a lot more efficient. In devices where heat is produced, the major concern is heat loss. So adding more insulation can improve efficiency. So when I'm thinking about my home, if I want to increase efficiency in my home, okay, I've talked about getting a better furnace, maybe a better hot water heater, but then I got to go into the more complicated stuff. So, you know, maybe I need to start ripping down walls and putting in better insulation. Probably not a path I want to go down right now, but I do have an attic, and that attic is full of insulation, and maybe I need to do a better job of insulating the attic. So there's lots of ways for us to increase efficiency in it, and a lot of the work in engineering and science right now is looking at how we can get better and use our energy more efficiently as time goes by. So that's it for concept D4. At this point, we're just shy of 40 minutes. You can go and have a look at the questions in your textbook. And then there is a worksheet that's a continuation of D3. So go in there and jump in and see if there's any questions that you missed because I said to you last time you couldn't do them because they were from concept D4 or 5, get that done. I may or may not have an activity up there for you, so check for that activity. If it's not there, you don't need to do it. If it's there, have a look at it, do it, please. And then once you've done that, please move on to the formative practice quiz. Do the practice quiz, and then wait for my feedback before you move on to the summative quiz. Thanks for watching this sort of discombobulated video on energy and power and efficiency. If you have any questions, track me down online via the Google Hangouts that we do, or sorry, the Google Meets that we do every day for my office hours, or fire me an email and we can set up another meet if you want to, or just fire me an email with any of your questions. Thanks for watching, and we'll talk again soon in Concept D5.